Okay, where were we? Can we do another maybe 15 minutes here?
Yeah, sure. I am on.
Share my screen. Send request. Okay. Okay, so this makes sense then. I got it on definition two.
The next is a convex function. So we define a convex function like this, that if you basically evaluate the function of two endpoints and then evaluate at some point in between, then what did you get from taking the linear weighted averages of the two endpoints is more than what you would get in between.
It has to be above anything that's
Yeah,
yes.
yes.
That makes intuitive
That's
sense.
to be below, actually. The function has to be below the straight line.
Yeah, the straight line will be above anything because
Yeah,
even
straight
like
line. Yeah,
basic quadratic, right? Like
yeah. You can think of parabola as the easiest example.
yeah,
If you
yes.
can two points of the parabola, the curve remains below the parabola.
The curve bullet remains below. And because it's any point in between those 2 points then.
Yes.
And what you're saying from what you're saying previously, and this works in any dimensions as well too.
Yeah, this works in any case. So, for example, linear functions are convex. The quadratic functions are convex if the Q matrix is positive semi-definite. This is the most important fact for us. It is convex if and only if Q is positive semi-definite. Positive semi-definite makes number one, that all the eigenvalues are non-negative, and less important fact is you can take Q to be symmetric matrix always. So when you are taking quadratics, you can always assume the Q matrix is symmetric, which implies that the eigenvalues are all real numbers. Now, once they're real numbers, we can talk about positive, negative. If they were complex numbers, we not necessarily talk about complex number being positive or negative. So because we know the real numbers, the condition being that they has to be non-negative. So negative eigenvalues are not allowed.
The positive makes sense. Can you define the semi-definite? What does that mean
Oh,
again?
semi-definite. So positive means all the eigenvalues has to be positive.
Okay.
Semi-definite means zero is also allowed as an eigenvalue.
Okay, got it. Okay.
Okay? So that's like semi-definite. So
Got
some will be positive, some will be zero.
Okay. Okay. Where did this, oh, this equation is just the equation of
The
a,
definition of a quadratic function. So this is like the corresponding thing of ax square plus bx plus c.
that's,
So that ax square term, now instead of you have x transpose and x, that is the x square, and A is becoming a matrix now, which is the Q matrix.
how did the half come there? I'm curious.
Oh, the half is so that when you take derivative, you don't have a x square derivative has 2x.
Oh, right,
Here
right.
the derivative won't have the 2.
Yeah, so then you
So
multiply.
just to adjust for that.
Okay, got it.
So derivative of that quadratic will be just qx plus b.
Oh, because yeah, x squared, so qx
Yes.
plus b. I
Plus
know
b.
I'm reviewing the one thing that we didn't do, Sujay, on the
Yes.
linear algebra review was the derivatives of matrices. That was one that I don't remember that we did on there. So that was one I'm
I gave you the quick formulas, but I don't think we did the proof
okay.
and
Okay.
detail
Okay.
that.
I need
If
to
you
remember
get
those.
stuck anywhere, let me know. I can explain
Okay. Yeah.
those
It's
two,
just
three lines again.
remembering. Yeah, it's just
Yeah,
remembering those
yeah,
facts, though.
it's
But
just
yes, what
remember.
you said
Yes,
checks out because I was doing those for the
yes,
homework,
yes,
and then the derivative makes sense there.
yes. But yeah, make sure that you really understand those things because we will use them all the time.
Okay. Okay.
And as far as convex optimization goes, understanding quadratic function is very important. That's basically all the intuition comes from. So all the
Yeah.
examples, all the
Yeah.
intuitions, all the geometry is for quadratics. We don't
Yeah.
really understand cubics
Yeah.
in matrices. And the reason is, I will tell you. So you see that the C is a constant, which is a scalar number here, right?
Right.
B is a vector.
Right.
Q is a matrix.
Right.
Now, if you want to add a cubic term, it will be the higher thing after matrix, which is a tensor,
Yeah. Got it.
which
Yeah.
is difficult to imagine even with maths.
That makes sense.
So try to understand up to this level, like really concretely. The rest, like people will do some notices who won't understand.
Got it. Okay, that makes sense. Function f is convex and q is positive semi-definite. Okay. Any norm is convex. This follows from the triangle inequality and homogeneity scalability.
Oh, the homogeneous part that is talking about is basically norm is same in all directions. So when you do basically a unit ball of radius r, it is radius r in all the directions.
Oh, yes, because that comes
As
from,
opposed to ellipse kind of thing, which is like fatter in one direction and not fat in other direction, that kind of thing.
yes. Okay, got it. Cool. Any local minimum of a convex function is also a global minimum. We now turn to first order optimal conditions. And we first state that proposition.
Yeah, so this is some alternate uh, ways of stating some convexity.
But like if I have some complex, how did you write? Can I draw some complex function here? Where's
Yeah,
the
yeah. You can,
more
you have annotate button right above your audio button, top, bottom left.
dictate? Unfortunately, don't see that. But let's just if I have some complicated function that has a lot of curves in it,
Yes.
how are we defining that a local minimum I can find, oh, of a convex function, a
Yes.
local minimum of the convex function.
So the non-convex function can be
That's
like this,
not convex.
which can have multiple local minima, one here and another here. But convex function cannot have this kind of situation which has two
Notice
local minima,
from the previous.
and they are of different levels. So like this is a global minima, and the right one is not a global minima, right? The left one is a global minima, the right one is not.
Maybe this is a dumb question. Can you
Yeah,
draw a convex function that's not quadratic
yeah. So let's say
or linear? A convex function that's not linear or quadratic.
this is not linear or quadratic.
So, but it has to kind of follow that parabola shape then?
No,
Because I'm having a hard time imagining a function that
imagining what
has,
functions? Okay, let me do it and draw that. So imagine what a convex function can do. Mm, So let me give you small examples. So for example, y equals absolute value of x is convex function, which is the linear thing, right?
yes,
And then y equals x square is also convex, which is the parabola thing.
yes,
Okay. You can take x power 4 also, which looks like something like this. Okay.
yes,
And then x power 6, x power 8, and so on also.
got it.
Okay. So all of them are kind of like a bowl kind of thing.
Yeah,
Okay. Now, what can we change really? We can, first of all, make this asymmetric. So you can choose the x square on the left hand side and x power 4 on the right hand side. That is possible.
oh,
Okay. You can also, so x square, if you think about it, x square is basically saying that the second derivative is always 2.
yeah,
If function is x square, the second derivative is 2 everywhere. It's a constant, right?
yes,
So a convex function basically requires that the second derivative is positive.
yes. That's from calculus
That's
one,
like
right?
another calculus equation, yes.
Yes.
So, but you can change what that positive value is. It can
Um,
be 2 somewhere, 5 somewhere else, and so on.
yeah,
And that basically gives you a lot of flexibility in terms of what the function is.
that makes sense. Okay.
If it's x power 4, then the second derivative is 12 times x square.
Yeah.
Okay. Which again is a specific kind of function, but it doesn't have to be that specific. It can be, you have a lot more freedom. So in that sense, convex functions have a lot of freedom.
You're using the even powers, but I feel like even for x cubed looks like what? X cubed looks like this.
You have to take absolute value of x cube to make it work. Then it works.
Why?
because otherwise x cube goes negative. So x cube looks like this.
But
So
I
here
thought
it
we
will
said
come in
that
between,
I thought that
and
we
then
said
this.
that y is equal to x is a convex function. The linear functions
No, y equals absolute value of s is a convex function.
y is equal to
If you
so
don't take the absolute value, it's a straight line.
we can't have negative values then? Did I miss that?
We can have negative values, but we cannot have so x cube. If you take the second derivative, it is 6x, right?
Yes. Yes.
So
Which
6x is positive for the positive part, negative for the negative part. So the
right.
second derivative cannot be negative. So actually, x cube is doing something which is the positive part is convex, but negative part is concave. It's the upper other, like it's a reflected
Yeah,
convex.
yeah, yeah.
So you take the absolute value to reflect it upwards.
Got it.
So then it becomes this, and you get a convex.
Got it. Okay. 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 Sorry. I
Okay.
was just having a
No
trouble.
worries. Yeah.
Okay.
So you can remember this that second derivative has positive. That's the restriction. Otherwise, the second derivative value can be anything anywhere. And locally, like within a small interval, convex functions always looks like x squared plus something.
That's what I'm thinking too, because anything you're drawing here, it's pretty
Yeah,
much
it's kind of like x squared, but some scaling factor and all that.
yeah, it's gonna shoot up faster at some points then too, right? Yeah.
Yes.
Okay. Okay.
Okay.
I don't know if this is anything similar, but this is reminding me of exactly what you did previously with the norm ball. Like it starts out like this and then just slowly becomes
Exactly. Yeah. So this like yeah, they are related actually.
yeah, okay. Okay, that makes sense. Okay, sorry, I lost my place. So any local minimums. Okay, so then that definition makes sense. Any local minimum is going to have to be the global minimum then as well too. Anything else I should know on this one? I don't remember. I remember Taylor expansion is a way to expand for a series.
Expand a
Taylor
function in terms of series of its derivative terms.
series of its yeah, you can write a function in terms of its in terms of the series. Yeah.
And basically, if you stop at the second derivative part, that is like the quadratic expansion.
Quadratic expansion.
And yes, for convex functions, that is basically we can deal with the quadratic approximation. Like if you, even if you ignore the higher order term, so up to that, if you understand the function well enough, then that's basically good.
Okay.
That's what we say.
Okay. Nice.
Okay. Yeah.
This looks very similar to this one here. Is it the same? No, it's a little different.
No, it's not. It's kind of related. So think of this. Let's say y minus x is h in this proposition 2. So then what we are saying is f of x plus h is f of x plus greater or equal to f of x plus h times the derivative. So if you're doing Taylor series, then what you have is f of x plus h is f of x plus h times the derivative plus h square by 2 times the second derivative plus
Yeah,
so on, right?
I remember that. Yes. Okay.
So, yeah. So what this is saying, because the h square over 2 into second derivative is positive for convex.
Yes.
So h square over 2 into second derivative, this thing is positive.
Positive.
And then the higher orders are less important if you choose h to be small enough.
Yes.
So it is saying that this is equivalent property for convex.
That makes sense. That makes sense. So this is the Taylor expansion part right here.
This is the first derivative of the Taylor expansion curve.
Is oh because yeah,
And it is saying it will be above. So this is another way of saying that it is always above the line. So at point x, if you
oh
draw a tangent, then my function is above the tangent line.
yes. Okay. Oh, like this. I think he
Got the
puts the
picture?
photo here. Wait, he had
Yeah.
a
So if you have this, and then I draw a straight line
yeah.
passing through that,
It has to
then
be
it is
the function exists
always
all
above.
above that line then.
And you
Oh,
can draw the tangent at any point, and it is always above the tangent line.
okay. Okay. Got it. Okay.
And the corollary is if the derivative is zero somewhere, then it is a global maximum.
Yes, because that'll be at the lowest point here where we get to
Because
the
then, yeah,
derivative equals
yes,
zero.
the tangent will be flat, so everything is above that, so you cannot get any lower.
Okay, got it.
Okay, so this is all of this is basically to prepare ground that it is okay to do derivative equals zero for optimizing. For first, like the ordinary maximum minimum problems, that's what we have been doing all the time, right? If you have
Yes,
to optimize a function, set the derivative to zero. So
easy.
this is saying for
But
convex function,
yes,
convex differentiable function, it's okay to do that.
okay, that's a good point. So it has to be convex differential, but do we deal with concave function? Oh, wait, I think somewhere it just said just make it negative then, right? If it's a concave,
Yes, but there are functions other than convex and concave.
right?
Those this theory doesn't apply, and that's the reason you are having a separate lecture on convex optimization, because within convex optimization, derivative zero trick works,
Works.
and so a lot of theory works.
So this isn't the end of it. It keeps going.
Yeah,
Ooh, okay. Okay, I think this was a really good review of these things. Can we pause here? Are you free tomorrow? Hold on, I'm gonna pause the recording. Are you
yeah,
free
yeah. Okay, cool.
tomorrow, Sujay?
Yeah, yes,
Tomorrow, can we do gradient descent? I think that would be because that's the last topic that we've done in
yeah.
class.
That's the important part.
If we can do gradient
Yeah,
descent,
gradient descent is not a large topic or anything. It's just
it just introduces a lot more things like alpha, K. Now we have a variety of
yeah, yeah.
different.
I will give you the geometry of it. I think
I
that's
can
what is
because
good.
we did it in Python and it makes sense. Like we just keep taking steps as we go down, down, down. And like I think conceptually it makes sense, but
Yeah.
the the formulas aren't as intuitive, I guess. Because now we've gone into logs and stuff too, which I don't really
Yeah,
understand what those.
those I would say, just think of it that there is a formula. If someone wants to calculate something, people don't actually use this formula to do anything meaningful either. It's
Got
just good to know that this formula is telling you something.
it. Okay, got it.
You never need to use it.
Okay.
Okay? But like, what are the implications of this is more important for us. So
Yes.
implication of this is basically that if I'm trying to do an optimization using the derivative, then my rate of convergence is linear or geometric. Both the means it.
Can you say
And
that
what that
again?
linear means is basically.
I'm sorry.
So
Can
what that linear means?
yeah.
So let's say I'm optimizing something, and so y equals function of x. I want to find the best value of x, right?
Yes.
So let's say I want the correct value of x up to 16 decimals or
Okay.
up to 100 decimals, something like that, right?
Okay.
In real life, you never want the full, like you don't want infinite decimals. You only want up to certain decimals.
Right.
So then people want to know how many iterations I have to do.
Oh,
Okay.
okay.
And more importantly, so suppose I have reached it 5 decimals and now I want to improve to 10 decimals. How many more iterations I need to do?
Okay.
Okay. So this is saying that number of decimals versus the number of iterations, there is a linear relationship.
Oh,
So it's probably that like every iteration will increase the accuracy by one more decimal or two more decimals, something like that, linear sense. Whereas the next optimization method that we will learn, which is Hessian based, which is has a uh, quadratic kind of thing, which means that if after certain number of iterations you have got 10 digits correct, next iteration will make it 20 digits correct, and the iteration after that will make it 40 digits correct.
that's
Okay.
pretty cool.
Here, maybe you will increase by 3 decimals every iteration. There, it will double whatever the number is. So once you have reached at least 3, 4 decimals, it will converge very, very quickly.
Got
Your
it.
accuracy will grow very, very fast.
Oh,
So that's
interesting.
like the important thing to compare and remember against.
That's
That's all you need to know about this
great.
convergence rate and all those things.
Okay. Okay.
Okay. So, like if you are dealing with Python or something with a double precision arithmetic, which is the standard, then you typically want 15 or 16 decimals. So in quadratic convergence, which will the Hessian based methods do, once you reach 8 decimals, you are very happy because one more decimal will be 16.
Yes.
Here, if I have reached 8 decimals, I don't know, I may have to do 3, 4, 5 iterations now.
Okay.
There is a linear relationship. How much every iteration depends on certain things, so there's no clear way to know that, but roughly that is the case.
That's pretty cool, actually.
Yeah. So that's basically all the conceptual thing that you need to know.
Okay, great. Then maybe tomorrow should we start on the logistic regression then? Because that's the next topic that's going to be there.
Yeah, we can do that.
Logistic. Let me open this real quick just to see.
Yeah.
I've
Just
sent
to
it.
show me
I sent it to you
quick
as well.
overview of what is covered there so that I know.
Yes, I sent to the document to you as well on how many pages?
Okay.
5 pages, so
Okay.
not too bad.
Okay. 5 pages. So let's see. This is good. Yeah. Scroll down. Next page. Yeah. Keep scrolling. Yeah. Fitting a model is good. Yeah. You do the log likelihood. Yeah. This is the binomial stuff. Scroll down. This is just binomial. Yeah. Yeah. It talks about entropy a little bit, which is good. And discuss that a bit. And then it's saying we do gradient descent. So you derive a formula for gradient descent, which is nice. Let's scroll down. Okay, and then we prove the convexity by doing the Hessian theorem. That is also good. Yes, that is good. And then there is a multi-class. Yeah, this is the more tricky part. We'll spend more time on it. So this is called softmax. Yeah, these are very important.
Nice.
So nice thing is the convex optimization theory can be applied here.
Teamwork here. That's what I'm seeing too. Yeah. Okay. Cool. Okay, I think we're
Okay,
progressing.
we'll continue here.
Yes, can we do this tomorrow then?
Yeah, we'll cover all.
Okay, sounds good, buddy. Thank you so much.
Thanks.